Welcome to the 2021 Virtual ARM Dev Summit. My name is Frank Schirmeister. I'm leading the solutions and ecosystem aspects at Cadence Design Systems, and I'm here together today with Max Hinson from Greenhill Software. He's a lead technical marketing engineer. So the topic today will be the acceleration of safety and security verification for ARM v9-based systems to the pre-silicon phase. Greenhill Software and Cadence are strategic partners with really interoperating quite a bit when it comes to the software development and security aspects. And what we have planned today is a brief overview of the hardware-software development challenges, the system complexity as it grows, the costs of defects. Max will walk you through the significant challenges around safety and security. And then I'll take it over back from Max and talk about the abilities design teams have today to move the hardware software verification to the pre-silicon phase, specifically using different types of execution engines there before silicon is available. And then we'll drive it home with some examples of what we have done together. So let's start with the hardware software development challenges. When you look at complex systems, like in this case, a car here, a lot of things have to converge successfully here when you look at hardware and software together. So you have in the bottom of the system here, typical ADAS type system with a set of cores for compute. You have some specific accelerators. You have lots of peripherals and interconnects. And on top of it, you have various levels of software at the lowest level, hardware abstraction layers. And then you have different operating systems like Linux and Android potentially running on top of it. And when you think about how these interact, especially at the interface between hardware and software, there are a lot of things that need to be validated early and that can potentially have impact on safety and security. Here's a effort slide talking about hardware and software development efforts together, and my German genes are rebelling a little bit because I should have attributed this here, and I'll do it here with verbally, to Handel Jones and IBS. This is the 2020 data he presented. And what you see on the right there, especially for advanced designs, the development effort in a context of a chip design of hardware and software, and specifically its verification. So that's the greenish portion with prototyping involved as well. And then the verification of the hardware. If you look at the progression over the different technology nodes and switching from mature to advanced designs, it is a amazingly complex set of effort estimates that the analysts have here. And we see this day to day with project teams we're working with. There's a lot of software and hardware interaction to be verified. The challenges in a hardware software system include really the low-level software potentially, which you see in the center here for customer specific application-specific components, which have bare metal software, which the user never may see. But then you have for things like the communication stack, we see level 1, 2, 3 software here in the hardware abstraction layers, and then the software which the user sees directly, the operating system that boots on our phones or that boots in our car. You have a lot of interaction going there, having to deal with the I/O, with the system infrastructure, lots of cores and symmetric and asymmetric configuration, and then lots of software, some of it being, as I mentioned, part of the core functionality like drivers, but then also the user application software. And if you look at the impact that a bug that slips through may have, it is very significant. If you look at the classic V diagram, and we're not walking through all the values here, but the key message is the later you wait, the later you find bugs in the system, the more expensive they will be to to correct. And you see this both in the software and the hardware world happening. So on the right-hand side, a slide here talking about how the impact relatively grows if you find it out at the customer side relatively to removing bugs, hardware and software, early on before you actually get your design out. And with that, I'll hand it over to Max to talk us a little bit through the safety and security challenges.
So safety and security is an incredibly broad topic, and it could fill many, many presentations. So I'll just cover a few points in this section that I think are most critical to pre-silicon development of safety and security critical systems. It's well known that safety and security need to be designed in from the beginning, not added later after most of the development has already been done. So there's really no better time to begin developing safety and security critical systems than the pre-silicon stage. I'm going to start with chain of trust. The main idea behind chain of trust is that the security of each layer relies on the security of the layer below it. So at power on, the hardware needs to securely run the bootloader, which needs to securely run the operating system, which needs to securely run the device drivers, and so on, all the way up the software stack. Secure boot is a critically important technology in that it allows the hardware to run only signed or trusted software images. That's enough for us to trust the chain up to the operating system level. However, secure boot alone is not enough to guarantee security. After the operating system is running, we're in the runtime software domain. Some embedded devices are designed to reboot rarely, or sometimes not at all, which means the device may be in this domain indefinitely. In the runtime software domain, the security of the entire software stack depends on the security of the operating system. If an attacker can compromise the operating system to run arbitrary code, secure boot is not going to save us. So in order to keep the chain of trust intact, the operating system needs to be robust to application programming errors and malicious attacks, and must also be able to securely apply over-the-air updates to run new application software. And now we'll move on to the role of the operating system and software architecture in building safety and security critical systems. As processors continue to gain performance and more software functions are consolidated onto a single hardware platform, it's incredibly important to manage that complexity with the proper software architecture. This diagram is an example of what many of our customers are building in their production systems today. At the lowest software level, there's the certified separation microkernel real-time operating system. This is the foundation of the software. A separation kernel provides isolation between virtual address spaces in user space, so that if one application crashes or gets hacked, the damage will be contained and its effect on the rest of the system will be limited. A microkernel contains only the minimal amount of functionality to host these virtual address spaces, which allows the kernel to be smaller, more robust, and easier to certify for safety and security. Combining these two properties together, we have an operating system that can achieve the highest levels of safety and security in the world. At the user space level, we have device drivers and native applications that are deemed critical for one reason or another. They could require real-time responsiveness or safety or security guarantees. And they're kept isolated from each other by the separation properties of the underlying RTOS. Additionally, virtualization can run as a service on top of the RTOS. The virtual machine monitor runs in its own virtual address space, providing an environment for a high-level operating system and its applications. The software that runs here generally relies on large open-source software components, is not safety or security critical, or does not require real-time guarantees. This architecture is what we'd expect to see in a production system. However, oftentimes, pre-silicon software development is done in a prototype environment using a general purpose operating system like Linux with no timing guarantees or separation capabilities. And it's often simpler to download and run open source software to begin prototyping, but that can quickly build up technical debt that must be paid off later when the development team must switch to a more production-grade environment. The integration of the production-ready architecture and applications often happens later in the software development process and introduces issues that are more difficult and expensive to fix, as Frank showed earlier. By using production-grade software in the pre-silicon development phase, development teams can find issues earlier and get to market faster. Of course, finding and fixing bugs is a critical part of developing safe and secure software as well. And in complex systems like this one, there are many levels of abstraction between the layers of software, and fixing bugs may require debugging at multiple layers of the stack. So it's important to have software development tools that allow you to debug your software at all levels of abstraction simultaneously. At the lowest level, that means using JTAG, Caddy, Iris, or other freeze mode connection to halt the physical cores and debug the RTOS kernel. At the user space level, that means using a run mode connection over Ethernet, for example, to debug your device drivers, native applications, or virtual machine monitor while the physical cores continue to run. Next, you can use a virtual freeze mode connection to halt the virtual cores and debug the kernel of the guest operating system. And finally, you can use a separate run mode connection to debug the applications within the guest OS. Having this capability across heterogeneous multi-core hardware, combined with visualization of trace data and backwards in time debugging, allows you to better understand your complex systems and find and fix bugs and performance issues much faster. For those who are not familiar with Greenhill software, safety and security critical systems have been our focus for the last 35 years. Over the years, we've built world-class software development tools and runtime software that are certified to the highest levels of safety and security in the world. But the proper development tools and runtime software, while they're essential in developing systems, there's still more to the process. In addition to products, we also offer services to our customers seeking safety and security certifications. Having been through these certification processes many times ourselves, we can help with things like safety and security case analysis, software development, training, and certification support data. With this combination of products and expertise, we've achieved the highest levels of safety and security certifications and enabled our customers to deploy safety and security critical applications in a wide range of industries. These include ISO 26262 ASIL-D in the automotive industry and DO 178B and C level A in the avionics industry, just to name a couple. And as I mentioned earlier, it's critically important that safety and security be introduced in the beginning of the development process, not added later after most of the development work has already been done. So with that, I'm going to hand it back to Frank to discuss how safety and security critical software and tools, like the one I've described, can be used in pre-silicon system development.
Wonderful. Thank you, Max. So let's dig into the combination of hardware and software verification a bit deeper here over the next 10 minutes. If you look at the complexity of the systems, and you saw Max describing the different levels of OSs where You want to be able to debug and do these freezes, these really points of stopping things, looking at things, looking at defects if hardware software elements go wrong. If you look at the stack, that of course continues in the bottom through the hardware, the system, the board, the system on chip, and the IP blocks in the chip, like the processor cores. And the reason we are here at the ARM Dev Summit is obviously the ARM processor cores, but there are many different cores typically on a chip, as you can see on the right here. During the development, you often do not have all the components available at the same level of abstraction. Some of them you may have hard IP, you may have licensed them. For some of them, you may have the actual silicon available. For some of them, you may have a model which is just under development at the transaction level. That's what we call the TLM model. So in a system environment, you have different components available throughout time, and you really need the ability to switch the different dynamic engines you use for verification and software development as productively as possible. When you look here at this particular slide, the different engines we are showing here are going from the very left, the software development kit. So something like a phone development kit for Android would be a good example. They have very high speed, but they really abstracting the hardware quite a bit. You then have what we refer to as virtual platforms. They are almost at speed. They're fairly fast in the range of what software developers get happy with. The hardware functionality is accurately modeled, and then there is often a question how accurate timing is modeled in this. The function is always accurately so that the software can access registers, for instance. But about timing and things like this, there are different versions which allow users to make hardware software development assessments, but the speed needs to be taken into consideration. And the other engines here on the right-hand side include engines that are traditionally used for hardware verification, like the HDL simulation, which really gives you really good hardware debug. You see the waveforms here, but it's often too slow to run full software on top of it. For that, people use acceleration and emulation, which is a good combination of speed and debugability into the design, being able to observe it. And then you have FPGA-based prototypes and eventually the full-on prototyping board when the chip comes back from the fab. And what you really are trading off here is the early availability to the left versus the accuracy as the design matures and you get more details. A virtual platform, which is key here, and we'll talk about that a bit more, it's really an instruction-accurate software model. So it's running the same software you would load using an ELF file at the end into the board. It has a programmer's view of the design, runs unmodified target code. And I'm introducing a term here on the right-hand side. The speed goes up the higher you go in abstraction, but the accuracy goes down, and it also takes longer to get to the model. So people are looking at combining different levels of abstraction in a what we call hybrid fashion here. And so you have here then the example of a virtual platform, somebody in the Bay Area really sending data through a network and looking at the results on a virtual graphical user interface. We're using, during the development, to move all this into the pre-silicon phase, the techniques to either use different performance level by way of platform used. So the simulation platform based on the Excellium technology here is really software-based. You run it on a host. With Palladium emulation, you have a dedicated, optimized supercompute environment for emulation of the hardware, where prototyping is even faster than emulation by typically a factor of up to 10 times. It's based on commercial FPGA. So you are in the hertz range on the left, the megahertz range in the middle, and the tens of megahertz range on the right. That's one way to get performance. The other way to get performance is to use abstraction. And that's really where this hybrid situation comes in that I mentioned, where you have a pure virtual platform which is executing on a host, on a virtual platform using, for instance, the ARM fast models, and you combine that in a hybrid fashion with some of the hardware blocks mapped into hardware, and you can simulate them, emulate them, or prototype them. So that gives you performance variations and accuracy variations using multiple levels of abstractions and combining different engines. To put this in perspective, here's a chart of the Linux kernel map. That's a quite dated chart, but the principle is probably very clear. It's fairly complex when you go to the lower levels, and that's really where a lot of the issues happen at the hardware-software interface. What people typically do not do on virtual platforms with that level of accuracy is the high-level application developments. You will make some assessments, but you're really focusing on the hardware-software interaction up to middleware typically. So we have good examples from customers like NVIDIA doing, for example, the OpenGL graphics in a hybrid setup. When you then look into doing all this pre-silicon and a typical setup for hardware and software, here you see the design we had mentioned earlier with the different software components running on it, like, for example, the integrity software environment from Tensilica, from Green Hills, mapped onto the chip. That's mapped into the various platforms, virtual, FPGA-based prototyping, and emulation. You connect it through probes. Max mentioned earlier things like CADI and the physical probes on the right-hand side, and you have probes for connecting that to the hardware debug. And that gives you an environment in which you can really bring together the software debug with the hardware debug at the lower level, up to some system debug aspects, looking at thread analysis at the software level, and looking at performance aspects at the hardware level, looking at things like buzz bandwidth. So as Max already mentioned, the levels of abstractions here and combining them appropriately are very important. So here you get the different levels of lower level hardware software debug and up to the thread level and the performance level debug aspects, all in a unified environment. And to bring this home here over the last 1.5 minutes, there are several examples out there which we have as Cadence seen, some of them together with Green Hills. We'll talk about that here in a second, but you see different different cases here, like Ericsson presenting at CDN Live about purely virtual environments. ARM, actually, in this case, being a user, this is ARM looking at some of the AI components, getting significant speed up compared to RTL, again, trading the virtual and the hybrid versus a pure RTL hardware performance. You have Bosch in the automotive domain, OS bring up for Linux and Android as shown by NVIDIA here. So you have a large number of examples of how you put together these different environments between pure virtual, pure silicon, and the emulation, prototyping, and hybrid aspects in between. One example we are happy to follow up with, and we have a demo for. Max actually has been showing this quite a bit. This brings in together Green Hills, ARM, as we are guest today here at the ARM Dev Summit, and Cadence by putting together a virtual platform that runs in the Cadence environment. This is very similar to what ARM would refer to as the versatile platform, Versatile Express platform, that's using ARM fast models running in the Cadence environment is here you see the debug, the software debug attached to it, and you see the little penguin here showing how the OS is booted in a pure virtual environment. So with that, that's really the end of the presentation. Thanks for your attention today. So bringing together really the safety and software security aspects, as Max pointed out, and then having the ability to execute them early in pre-silicon engines, as mentioned, virtual prototyping, simulation, emulation, prototyping, and then bringing together the different technologies for hardware debug and software debug well before silicon comes to market allows you to really move the assessment to the left, as the industry calls it, and allows pre-silicon assessments of the safety and security aspects. With that, thank you very much. Thanks, Max.